Hi everyone, let's work on learning catalytics 8121 gas properties and ideal gas law. If you hear noise in the background, they're my awesome coworkers. I'm in their classroom, so I'm their guest. Let's work on question 1. It says, when a scuba diver descends to 10 meters, what is the increase in pressure, that is, the change in pressure? Acceleration due to gravity is 9.8 meters per second squared, and density of water is 1,000 kilograms per meter cubed. And we have a hint. That is the equation, the formula for pressure based on density and height. So let's start with our given as usual. So we have 10 meters, and that is the height. Well, since we have to find the change in pressure, Brigletto delta, we need to have something final and then something initial. In this case, and that's the end point, meaning she's going to go down up to 10 meters, we can consider that as the final height. H final, 10 meters. And then acceleration due to gravity, 9.8 meters per second squared. And density of water, 1,000 kilograms per meter cubed. Now, what is the initial height? Well, we're going to establish the initial conditions that at sea level, the height is 0 meters. That's our starting point. Height initial is 0 meters. And we have to find the change in pressure. Well, notice that the acceleration due to gravity and the density of water will not change from going to 0 meters to 10 meters. Water is water, and the acceleration due to gravity is a constant. Meaning, our formula can be written like this. Density, acceleration due to gravity. Again, the only thing that can change and will change is the height. Meaning, we're going to write change in height, delta H. Delta, final minus initial. So we'll continue, same thing. Density times acceleration due to gravity times height final minus height initial. And that is very, very simple to do, right? Height initial is 0 meters. So now we can substitute. We have density of water, 1,000 kilograms per meter cubed, times acceleration due to gravity, that is 9.8 meters per second squared, times 10 meters. So in this case, since we're multiplying times 1,000 and times 10, I'm just going to move the decimal point 4 spots to the right. So that would be 9, 8, and then 3 zeros. And I'm going to rearrange the units because I want to show you how they cancel and then we end up with pascals. So we have kilogram times meter divided by second squared times meters cubed. Meter per second squared, that is the unit for acceleration. Kilogram is the unit for mass, so it's mass times acceleration, that is force, meaning the unit of force is the Newton. So in this case, we can say the pressure is 98,000 newtons per meter divided by meter cubed. Well, the meter and the meter cubed will give you Newton per meter squared. And that is what we know as pascals. A Newton per meter squared. So the answer is 98,000 pascals. Let's box it. There you go. Now, question 2. It says, if a diver were to descend to 10 meters with air in her lungs without breathing in or out, What would be the approximate new value for the volume of the air in our lungs? Treat the lung as 6.0 liter of ideal gas. Atmospheric pressure at sea level is 1.0 atm. Now this is a multiple choice. That makes it easier. So we have to analyze this problem. Okay. And what is it asking us to do? We need to find the new value for the volume of the air. So we're going to be working with volume, meaning new value. So we're going to be looking for final volume. Okay? Now, we have ideal gas, meaning we can use the ideal gas equation. So let's start with our given. So we have descent to 10 meters. Well, from question 1, we know what is the change in pressure, and now we know what the atmospheric pressure at sea level is. So pressure at sea level, that's going to be our initial pressure. Pressure initial, 1.0 atm. From problem number 1, we have change in pressure, that is 98,000 pascals. And then the lungs have a volume, so that's the initial volume of 6 liters. So well, they can hold gas up to 6 liters. So initial volume, 6.0 liters. All right. And we need to find volume final. Okay. Let's write down the equation for ideal gases. PV equals NKT. In this case, N is the number of molecules, K is Boltzmann's constant, and T is temperature. Now we're only concerned about pressure and volume. The number of molecules, when she breathes, it's going to remain the same, right? Boltzmann's constant is a constant, and we're going to assume the temperature stays the same because something's going to change for, in this case, the volume. Meaning we can say that pressure, volume, initial equals NKT, and pressure, volume, final equals NKT. In this case, both of these equal NKT, meaning pressure, volume, initial should be the same as pressure, volume, final. So we're going to do that. Pressure initial times volume initial equals pressure final times volume final. We can do very simple algebra to solve for final volume. Divide by pressure final. Then we have the equation, which is final volume. We'll do that again. Final volume equals pressure initial times volume initial divided by pressure final. How we can not just substitute our numbers, because look at the units for pressure. We have atm for pressure initial, and we have pascals for pressure final. So you have to convert either the atm to pascals or the pascals to atms. I like atmospheres better because they're not as big as the number of pascals. So I'm going to change the 98,000 pascals into atms. That is very simple to do. I'm going to pick green to show you the conversion factor, and we're going to do your favorite, which is dimensional analysis. So we start with what we have. We have 98,000 pascals. And then we know that 101,300 pascals, that's equal to 1 atm. Pascals will cancel pascals, and we have atm as our unit, which is what we want. So then will have 98,000 times 1.0 ATM divided by 101,300. So let's see what that is. 98,000 times 1. We're going to divide that by 101,300. I multiplied instead of dividing. Let me try that again. There you go. So 0.967, we're going to round to two significant digits, 0.97. In this case, 0.97 ATM. That is the change in pressure. So change in pressure equals 0.97 ATM. Well, we're not done because we need the final pressure, not the change in pressure. We know that the change in pressure equals pressure final minus pressure initial. We're trying to find pressure final, so we'll move pressure initial to the other side. We have that pressure final equals change in pressure plus pressure initial. So pressure final equals 0.97 ATM plus 1.0 ATM. So our pressure final is 1.97 ATM. Now we can find the final volume. So pressure initial 1.0 ATM times the initial volume, which is 6.0 liters, divided by pressure final 1.97 ATM. You notice how the ATMs cancel. We have liters. We need volume, so liters is correct. So that would be 1 times 6, we know it's 6, divided by 1.97. 3.045, so 3.05. That's our volume. 3.05 liters. Let's box it.